All right. Starting with our rules for differentiation. We actually have talked about this rule before. We talked about it as we did our formal definition of a derivative because we found out in that formal definition that every single time it was a constant in the top of the fraction in the limit that it took that number minus itself and we always got 0. So we've actually already seen this one, but here's your formal place to put that in our notes. If the function is a constant, the derivative of any constant is always 0. So as we look down at our example here, f of x equals 4, find the derivative or find f prime. And again, if it is a constant, I don't have any work or thought to do. The derivative of any constant is just 0. While you guys are writing that down, just kind of a little side note, again, continuing to tie the idea of derivative to the slope of the tangent line. If you were to think about the function f of x equals 4 or y equals 4, remember what that is. Y equals 4, f of x equals 4 is just a horizontal line up at 4, right? Well, if I were to draw at any point a tangent to this line, so let's say at this point I draw a tangent to the line, wouldn't that have to also be a horizontal line? So that's another way of looking at why is the derivative always 0 for a constant? Well, if it's a constant function, it's a horizontal line, and a tangent to a horizontal line is a horizontal line, which has a slope of 0. Okay, then this is what we kind of figured out during our warm-up today. The power rule and then the constant multiple rule. The power rule says this, that if you have a variable raised to a number, the derivative of a variable raised to a number, that exponent that was there becomes the leading coefficient, and then you subtract 1 from your exponent. Okay, it always will go down 1 degree. So let's do an example. A very basic example here. Let's say our function is x to the 5th. It's a derivative. The 5 slides out front, and we subtract 1 from the exponent. So the derivative becomes 5x to the 4th. The next rule talks about a constant multiple, and all that does is if there happened to have been a number, a leading coefficient of that x, that when we go to apply our power rule, we just multiply by the number that is sitting in front of x. So if we have a number sitting in front of x, a constant multiplier, a leading coefficient, that when I go to slide that exponent in front, those two will end up just getting multiplied together. So again, a basic example of that. Let's say our function is 3x to the 7th. Then its derivative, I would take the 7 times the 3 to get 21 and still subtract 1 from my exponent. So it would become 21x to the 6th. Now, it just took me all of 3 seconds to figure out what the derivative of 3x to the 7th was. Could you imagine putting an x to the 7th in our formal definition and having to write that out and 7 times and foil 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 over and over and over again? Okay, so we never did anything quite that ridiculous, but it's true. If you followed your formal definition, that's what you'd have to do. Thank God for our shortcuts, right? Any questions? All right, so take a second and work through these 6 examples, and I will say that you may want to talk at your table, especially about maybe letter D, but especially about letter F. See if you guys can get through those. I'll give you a minute to work on those, and then we'll go through answers. All right, let's go ahead and talk about our answers here. Again, I'm asking you to find the derivative of each of these using our new power rule. So remember, there are lots of different ways we can make a notation for a derivative. One of those is prime, so y prime. Basic power rule, move that 3 out front, subtract 1 from our exponent, 3x squared. We can write our derivative symbol as dy dx. That's asking you to do the same thing. 4 times negative 2 is negative 8. Subtract 1 from the exponent, x to the third. We can write dx of y, and then same thing, 1,000 times 10, 10,000. Subtract 1, x to the 999. Next row, this one sometimes catches people a little bit. When I do the derivative here, it is 1 times 8, which is 8. And when I subtract 1 from 1, it's x to the 0. But do we ever write x to the 0? X to the 0 is just what? 1, right? So and 8 times 1 is just 8. So we would not write that line, but that's what's happening, right? I did subtract 1 from the exponent. This one goes back to the first slide that we looked at. Derivative of a constant is always 0. Okay, and then the last one, I would, not to trick you, but just because we need to see it in different formats here, sometimes rewriting a function in a different, an equivalent form makes it easier to see. Not taking the derivative yet, but just rewriting it with the x off to the side, this would be the same thing as 1/3 x, right? And so then if I apply my power rule, 1 times 1/3 is 1/3. Subtract 1 from that exponent, you would not have you would have an x to the 0. So the derivative would just be 1/3. Any questions on that? All right. Our next one is what's called the sum or difference rule, and this one I think would become intuitive if we did this, and all it's saying that is if we're taking the derivative of a function that is a polynomial. Everything we saw on the last couple slides were monomials, just one term. But if we've got a couple monomials added or subtracted together, I can just take the derivative of each one individually, which allows us to apply the power rule to each one of those terms individually. So doing a basic example of a sum or difference rule, if my function were to be something like 4x to the 8th minus 2x to the 5th, each of those individual monomials, I can apply my power rule to each of those. So our derivative, let's see, 8 times 4 would be 32, x to the 7th, and then I do this a second time, 5 times negative 2 would be negative 10, x to the 4th. So basically I can just apply my power rule to each one of those individually as I go down the polynomial, okay? So you guys go ahead and try that on this one. Given this complex polynomial, find its derivative. All right, so going down the line, applying my power rule to find our derivative. 30 times 5 would be 150. Subtract 1 from the exponent, x to the 29th. 2 times 20 would be 40, negative 40, x to the 19th, minus 6, x to the 1st, plus 5, x to 0. And then remember that the derivative of the constant at the end is 0, which obviously we don't write. Any questions? Sheldon. It is applicable. Yeah, we'll kind of see, we're going to see some alternate forms, and you get to apply it the same way. Yeah, so negative exponents, it doesn't matter. We'll get to see that, and I think our very last example will show just that with a negative and where those can hide from us as well. Okay, yeah, we'll get to that. So we'll come back around to some of the hidden power rules, and that's where I think a negative exponent is kind of a hidden power rule sometimes. One of the other things in today's section is talking about horizontal tangents. Now, we actually have, again, mentioned horizontal tangents before when we were trying to draw the derivative given a function. And we found those horizontal tangents lying at maximums and minimums, right? If I hit the top of this and I were to draw in the tangent at that point, we would see a horizontal line. And at this minimum, again, if I were to draw in the tangent line at that point, I would see a horizontal line. And what you find out is that horizontal tangents to our graph are the same place as where our derivative has a value of 0. So how do we find horizontal tangents given a function? You kind of follow these two steps. Step number 1 is just find the derivative. Okay? So if they give you a function, to find its horizontal tangents, go find its derivative. And the horizontal tangents will be where your derivative is 0. So then after we found the derivative, we find its zeros. And how do you find zeros of a function? You set it equal to 0 and solve for x. So in general, horizontal tangents of our function are the zeros of the derivative. Horizontal tangents of our original function will happen where the zeros are of our derivative. And while we're kind of getting this jotted into our notes, I just want to point out, this is again where things can get a little confusing because we have now seen these words showing up and they all start to sound alike. Horizontal and vertical have showed up a lot, and also tangents and asymptotes. And those are easily confused for each other. So make sure you slow down and think about what it's asking you about. This is not asking about a horizontal asymptote, which I have asked you, right? And that was like the limit as x approached infinity, we got a number. This is a horizontal tangent. That is, if I were to draw a line tangent to my graph, it ends up being horizontal. That's where our derivatives are 0. So slowing down and paying attention to all those things that start sounding alike. So let's try one example where they ask us to identify the horizontal tangents to our graph. Where does y equals x cubed minus 4x squared plus x plus 2 have horizontal tangents? And then it says verify on your calculator. Now there's a lot of ways to kind of do the verifying part, and there's a couple ways actually to find our answer within this, but let's follow our steps. On the last page, I kind of gave you a roadmap of how to find horizontal tangents given a function. Step number 1 was just find the derivative. So that's exactly what we'll do. Okay, so we're going to find y prime. That's now a fast process, right? Because now I have my shortcut here using our power rule. So y prime 3x, remember always subtract 1 from your exponent, 3x squared minus 2 times 4 is 8, x to the first, plus 1 times 1 is 1, x to the 0, which we wouldn't write. So our derivative would be 3x squared minus 8x plus 1. Good so far? Step 2 says set our derivative equal to 0, solve for x, right? Find the zeros of the derivative. The zeros of the derivative are where the horizontal tangents of our function are. So I set this equation equal to 0, and then I have to go back to algebra, and sometimes that's our hardest step of the whole thing. I am trying to solve a quadratic for x. we've got options. First option would be to factor. Is that factorable? No, which means if it's not factorable, we have to use quadratic formula. Okay, so in case we ever run into something that is not factorable, remember how you can solve for x, quadratic formula, negative b plus or minus square root of b squared minus 4 times a times c all over 2a. Should give you two x values, usually. And this is ugly, so you're going to need a calculator and round to 3 decimal places. Okay, it asks us where these are happening, so that's an x value. Where does it have a horizontal tangent? If I go to my quadratic formula, it has a horizontal tangent at 2.535. It also has a horizontal tangent at 0.131. Okay, so the whole verify on your calculator thing, let's talk about that real quick. There's multiple ways we can verify this on our calculator and expect to see those exact same two numbers. One of those would go to the function itself. If I were to look at just the function, I would be looking for maxes and mins. And you have a function on your calculator that does that for you. So if I were to graph this in x cubed, it's going to look something like this. And we would have a max happening at 0.131. We would have a minimum happening here. So I could use my max and min functions on my calculator to verify that I found the right locations. A second option for looking at my calculator is I could look at f prime and find the zeros, right? So if I were to graph x prime, this guy, I would go find my zeros and find that I have a 0 at 0.131 and a second 0 at 2.535. So two different ways, and understanding, again, the relationship that's happening between those. Any questions for me on that? All right. The last little part here is I want to just make sure we kind of go through some hidden power rules. This goes back to our power rule idea. All of these can be done using our power rule, but sometimes it hides within the formatting of the function itself. For example, y equals the square root of x. Doesn't initially look to me like one of the ones we can do with our power rule, right? Because it doesn't have an exponent, but it can have an exponent, can't it? Square root of x, and this is a very basic one, but square root of x can be written as x to the 1/2. So this is not actually taking its derivative. All I am doing is rewriting this in a different format, and that is something we are going to do a ton in calculus, is understanding different ways that you can rewrite something, because then it will do something like make taking a derivative a lot easier for us, is if I know equivalent forms of the same thing. And now doing my power rule is easier. I've got a exponent here, so that says to multiply the leading coefficient by 1/2. So 1 times 1/2 is 1/2, and this is also now something we haven't seen before. My exponent becomes 1/2 minus 1. Well, what's 1/2 minus 1? Negative 1/2. Now, I would stop there and circle my answer if I was doing a free response question. However, I just want to continue to remind you of equivalent forms that we can see things, because if I were doing a multiple choice, that would not be the answer. So how else can that be written? This is again, algebra reminder that if I have something with a negative exponent, that I can move it to the other part of the fraction to make it a positive exponent, right? So I could drop that x down into the denominator. The 2's also in the denominator. And now it would be a positive 1/2. Or instead of 1/2, I could again turn it back into a radical. All three of those are the exact same answer. Okay, but understanding how to rewrite things and picking out the same answers. Questions on that? Okay, similar, let's try this one. Y equals cube root of x squared. So job number one is just remembering how can I rewrite that in an equivalent form so that it's easier to do with my power rule. So let's make sure that we are remembering our radical rules to exponent rules here. If I were to rewrite that, it would become y equals x to the what? 3/2 or 2/3? 2/3, right? 2/3. Why? Because it's still x squared. And the cube root is a 1/3. Well, 2 times 1/3 is 2/3. Okay, that's the same function. Now taking its derivative, 2/3 times 1 would be 2/3. Subtracting 1 from 2/3 is what? Negative 1/3. Okay, and then thinking through our options of equivalent ways that we could write that, just so we can continue to see other things. I could move that down into the denominator with the 3 to make that a positive. And then I could turn it back into a radical as well, all of which would be the same answer. Okay. Any questions on that? All right. And then our last equivalent form here would be one like this. This is also a power rule problem, which again, it does not initially look to me like it would be a power rule problem, but it's can I rewrite this in another way? And we, on the first two examples, talked about getting rid of a negative exponent by moving it. Well, now what if I move this out of here? I can put in a negative exponent, right? I can rewrite 1 over x as x to the what? -1, right? If I pull it out of the denominator, again, it will change signs as I move it from one part of the fraction to the next. So 1 over x is the same thing as x to the -1, which again, now it looks like it can be power rule, right? So following our power rule, to take my derivative, multiply by the -1, subtract 1, so -1 minus 1, -2. Right? Writing my answer, that works, or more commonly, they would actually clear out that negative and say that this is -1 over x squared. Any questions on that? All right. Your assignment is on page 124.